This is now diffusion probabilistic model. So diffusion probabilistic model is essentially the same model as we talked about right now, with where you consider your backward process, the reverse process, to be always a Gaussian. So it's always a Gaussian with mean mu and some variance sigma. Potentially you can learn the covariance matrix sigma, but in practice we don't do it. Okay? So you can, like the variational autoencoder, you can consider one network for your mean value, one network for your variance, covariance matrix. Every single time you're going to give the noisy sample and time into this. Okay? And then at the output you're going to get the covariance matrix and the mean value, right? So you can think about the model in this form. This is the most general form of DPM, but in practice we typically only learn the mean values. So we're not going to learn the covariance matrix. Okay? And then classical one is exactly the one which I showed you in the previous slide. So you have the mean value, which is learned at every single time, given the time and time index, the noisy sample and time index. And then you have the variance being something predefined, right? So you're going to say at time 5, the variance is 0.01. At time 10, it is 0.001, and so on, right? This is your choice. I'm going to give you some suggestion on the choice. Okay? So this is the DPM. And if you write down the DPM, the key point about DPM is that eventually what you're doing in DPM, in this model, is that you're really going backward in time by somehow subtracting the noise that you already added when you were diffusing. So every single time I have a sample with mean mu and variance sigma t squared, so I could say I have one random process. This epsilon is again 0 mean unit variance, right? So I'm going to multiply it to the standard deviation sigma t. I add it to that mean, right? This xt minus 1 is going to be this guy. This is exactly the one distributed condition to this xt and t. This is going to be exactly distributed Gaussian with variance sigma t, right? Sigma t squared, sorry. Right? Everybody's clear, right? So this is why we like this. And intuitively, this should be enough. Because when we started from data and we went forward, we just added noise, right? Added Gaussian noise. So if we want to denoise, it should be enough that we just subtract those noise, right? Everybody's cool? Okay. So you can simply implement it in practice. So you can consider this one. This is what we call a denoiser, typically. I mean, you might get the idea why this is denoiser, because this is just moving reverse in time. But we're going to see in a few slides why exactly we call it denoiser, because this is eventually doing just denoising for us. It's just subtracting the noise. You're going to see it. But the thing that is happening here is that you are getting xt, the sample at time t. Don't forget, you're also getting the time, right? Those of you who started with assignment 3, you do know how you can inject time into this neural network, right? You can embed it, right? You can just take t, just make an embedding vector, very large vector, and then you can feed it into your neural network, right? So you can get whatever the image was. You get one map of time, you just add it to all of those maps, and then you pass it through time, right? Pass it through the neural network. And you can even do it in every single layer, right? So every single layer, when you just process, say, convolution, and then you have a new output, again, you embed time and you add it. Key point, this time should be there. Somehow it should impact your neural network, right? Because from one time to another, the whole denoising process could change. Right? Everybody's clear? Okay. So this denoiser is going to get your time, and the noisy version xt is going to give you some mean value, right? Once you have this mean value, how you can compute the previous guy? So you are here at xt. You want to compute the previous one, xt minus 1. What you going to do? What you going to do to this mu t? You're going to add some noise to it, right? Clear? So you're going to say, okay, I have sigma t. I just sample one Gaussian noise. This Gaussian noise, this epsilon backward, right? Epsilon reverse. You just sample this guy, multiply it to sigma t. This is this term. Then you're going to add it to this mu t, right? So now this guy is distributed with mu t and sigma t squared, right? So this is very easy now to implement, right? Each time you compute the mu, the denoise version, you add some noise to it, and you move reverse in time. Everybody's cool? Clear? Great. So if you got clear, now, first thing, before we just go ahead and do the training here, let's think how we can sample from this one. Let's say that I trained this mu network for you. Okay? So I have done the training on mu. Now, you can give xt and t into this mu, and then at the output, you're going to get a mu, kind of mean value, which is a very good one when you want to do the denoising. Now, how you can do the data generation? How do you do the generation? You're going to start with one Gaussian noise, right? This is the one which is at the very end of the forward trajectory, right? And you move reverse, right? Each time you pass your sample on time through the network, you're going to get the mean value. You add some backward noise to it, and you go on, right? Everybody's clear? So you can write it down in this form. So I'm going to sample xt. This is now a latent variable, right? This is a variable starting at the very, at the very end of time, right? Gaussian noise. You're going to get this Gaussian noise, and now you just move backward in time, right? You start from t equal by t and then go to 1. Each time, what you're going to do, you're going to compute your mu value. This is going to be the value coming out of your neural network. So you get your complete noise, and you get the time t. You pass it through your neural network. A classical network that you might use is UNet. And then at the output, you're going to get one mu, right? Now that you have this mu guy, you're getting this mu, you add a bit of noise to it, right? So you sample this epsilon from a Gaussian distribution. You multiply it with the predefined sigma t's that you had, and then you generate your next sample, the one reverse in time, right? Now you have this guy reverse in time. Again, you give this one, and the new time index, which is t minus 1, you're going to give this again to your neural network. That neural network is going to compute you the next mu. You add the noise to that one, you get the second reverse in time sample, right? And you keep on going till you arrive at the beginning of time. That is when you have your data sample. Everybody's clear? Questions? Yeah.
For some reason, I feel it's still a bit counterintuitive that you're sampling, let's say the step 4 and step 5.
Okay.
You're sampling a noise.
Yes.
And then you add to the.
Yes.
It feels it's still a little bit counterintuitive.
Yeah, it might be, but it's going to get clear in few slides. Okay. Yeah, but right now, what you can think about is that that mu is actually having somehow the reverse impact of the noise, so that when it adds up with the noise, it's going to cancel out, and you're going to get the previous time step. You can think about it right now like this, but when we go on, especially when we make the DPM, then everything gets clear.
So right now, I can think of it as like, so the original noise value plus the new noise value
Yes.
times the variance. Somehow
Yeah.
it gives us, the sum somehow gives us.
Cancel out, yeah, cancel out with that portion of the noise. Exactly. You can think about it like that.
And then it somehow represents the picture that I actually want.
Yes, yeah, a noisy version of your picture. Exactly, exactly.
And we slowly move towards it until we
converge.
finish
Yeah.
the entire big T.
Yes, exactly, exactly. Question? Yes.
What is the sigma?
Sigma is something predefined. It's a kind of hyperparameter. I mean, at the end of the day, I'm going to tell you how. At the end of the day, you put it exactly as square root of 1 minus alpha, the one you use in forward, but you can't learn it as well. So the basic suggestion is to use the same thing as before, but you can just learn it as well. Just keep it as a free variable, and then when you write down the loss, you also train on that one. Yeah. Questions? No question? Great. So if you got no question, so this is the way that we are going to generate. Now the question is how we can train this guy, right? We have the neural network. We do know how the process of generation is working, but how we can train this guy? Well, I told you, you just need to keep in mind that particular loss function, right? That loss function, which you can compute with this network as well, you want to just minimize that one, right? So the way that you can do this is that we are going to just compute expectation over maybe one mini batch of the data. So I'm going to collect a batch of data from the data distribution. This is the batch of data from my data set, right? And I average this particular loss term that I told you over it, right? Meaning that for every single x0, for every single image inside my batch, I just compute this loss, and then I average them out, right? Everybody's cool? OK, cool. Now, this term that you see here is the loss function that I had, right? This is the one which we ended up last time. Every single time, the mean value, mu, is being subtracted from eta, and then this subtraction is added up over all the time, right? Potentially scaled with those noise variances.
Sorry, what is eta again?
Eta is this guy.
Oh, okay.
This is the posterior mean, right? This is the posterior mean that you can compute. So alpha is the one which you just came up with it, right? This was the one which you just added noise, right? So alpha is known to you. X0 is your data sample, yes, image that you have. And this xt is eventually the input to your neural network, right? Right? The input at time t to your neural network, right? So you can eventually compute this eta t. This is very simple, right? Everybody's clear? Questions? No question. Great. So basically what I want to do, I want to just compute this loss and average it over a mini batch, and then I just minimize it, right? OK, so one thing that I can do, I can get rid of that sigma, right? I'm going to write 1 over sigma squared to be omega t, right? So this is one weight for time t, which shows up here, right? And it's not important. I mean, I'm going to show you, I'm going to tell you later that in practice you can always put it 1, because the impact is very minor in all of your training. But you're going to put some omega t here, right? So what I want to minimize is this guy. Now you look at this guy and tell me if this is an easy thing to compute. And you might ask me, I mean, I guess the right question that you should ask right now is that what is the order of t, right? That capital T. How long is the trajectory? Now, I would tell you it's around 1,000. What do you think? Do you think this is a simple thing to compute? It's not, right? The main reason is that if you want to compute this guy, and at the end of the day you want to minimize it, this means that you need to move forward and backward on the neural network, right? But how many times you need to move forward and backward to compute one of sample losses? T times, right? Because you're going to do it once at time 1, once at time 2, and so on till capital T, 1,000 times, right? Every time you go forward and backward, right? This is very hard, right? So this is computationally huge because it's going to multiply all the process with a factor of time that you're considering, right? Everybody's clear? It's not changing the order, that's right, but it still is quite complex, right? Make it a bit less practical. Now, how we can get over this issue, there is a very tiny and interesting trick that you can do when you want to do that, right? And this is what we call the time sampling. So what is the idea here? The idea is that I can write down, I mean, I wanted to minimize this r hat, right? There is no harm if I multiply everything here by 1 over t, right? No harm. If I minimize 1 over t of this guy, I'm still doing the same job, right? So I'm going to write down 1 over t this guy. So I'm going to multiply everything by a constant, right? That 1 over t can go inside the expectation, right? Now you look at the guy inside the expectation. What is that guy? What is that blue term doing? Isn't that, again, an averaging over time? Isn't that? Right? So let me just consider t to be one uniform random variable, uniformly sampled from 1 to capital T, right? This means that the chance of every single time happening is 1 over t, right? If I want to just compute the expectation of this term under the summation with respect to t, what would it be? It's going to be summation for all t's divided by t, right? Everybody's clear? So, moral of the story, this term inside the brackets, this 1 over t, the blue operation here, is eventually the same as averaging over a uniform t, right? So this is like I just randomly choose one of the time samples from 1 to t randomly, right? And then I compute the loss term, the term under the summation, for that particular t. And then I do lots of it and average it, right? Okay? So my loss, empirical risk, final term, is expectation with respect to data, expectation with respect to time, this term, right? And the typical thing that we do in practice is that instead of computing the expectation explicitly, we just do it by sampling, right? So we can do the sampling both in time and data samples, right? So the thing that I can do, I can simply compute this guy by sampling. For instance, I'm going to define this particular loss function. So this loss function is now taking one sample x0, one time sample t, and then it's going to give me the term that I have inside the expectation, right? Clear? So when x0 and time is given to me, this is just one computation, right? So I'm going to randomly choose one time. x0 is given to me. I go once forward the network, come backward the network, right? And I have the gradient. That's it, right? Now, what is my empirical risk then? My empirical risk is eventually the expectation of this term, both in terms of t and data, right? And if I want to just do the expectation with respect to time, I'm going to assume that this t is random, uniformly sampled from 1 to t. Each time I compute this one and I average all of the samples, this is eventually going to compute me the time average as well. Everybody's clear? So you got the idea of what we are doing here? Questions? I'm going to show you in the next slide how you can now compute the loss. This is going to make it much easier for you. But the idea is that, I mean, at the end of the day, you're going to have lots of samples, right? Yes. Say, for example, you have 100 sample. If you wanted to do this one, this guy here, the direct summation, this one, okay? If you want to do that, this means that you take one sample and say you have 1,000 time steps, right? So you're going to just compute all of those 1,000s, and then you sum them up. Once you sum them up, you have one sample loss, right? You do it for all the 100 samples that you have, then you average them. You add them, divide them by 100, right? This was the idea, right, in the original one. Now, what you can do instead now, you're going to say, OK, I'm going to take the first sample, x0. I'm not going to compute it for all time. Uniformly, with the same chance, I'm going to sample one time, right? And I just compute the loss for that particular time, right? Then I'm going to have one of these guys, one of these losses for x0 and the particular time, right? But since I am sampling the time and data with the right distribution, data is coming from data distribution, time is coming from the uniform distribution, right? If I do it for all the samples and I average them out, this is going to be the same, estimator of the same thing, right? Yeah? So I'm going to use that one. Now, instead of going all the way over time, I'm just doing one time sample, right?
I think that makes sense.
Yeah. But, I mean, of course, the quality of your samples are reducing. But when you do it for a long period of time, like you do it for a lot of mini batches, then you're going to, at the end of the day, converge, right? Okay. Questions? So everybody's cool? So moral of the story, you can simply compute your empirical risk now by taking the average with respect to data and time of this particular loss function. And this loss function is now very easy for you computationally to compute on a neural network, right? Questions?
Yeah. Sorry. So, like, if it's in this case, if I still sample 1,000 samples, that the only advantage for this method is I can compute each sample parallelly.
No, you're not going to compute 1,000 samples. You are going to just sample for every single data point. You are going to sample once. Then this is one sample of x and t, right? Yeah. One loss sample for x and t, right?
So one data sample is
one time sample, right? This is one sample loss, right?
Oh, okay.
Yeah, but you average it over 1 millibatch. This is going to be an estimator for you, right? You compute the gradient, you keep on going till your data set is over, then you get back again at the beginning of data set, you again sample a minibatch. So you go over one sample multiple times, and each time you're sampling different time, right? And at the end of the day, you are going to converge to what you want, right? But this is more efficient as you wait for all the time to be over, right? That works. Questions? Okay, so if you got no question, then I guess this is the last thing that might be a bit unclear for you, right? And then this is going to be the way that you're going to compute the loss, right? So you're going to sample, say you have some data batch B, you have one denoiser mu, so you're going to sample one sample from your batch, so this is one data sample. Then once you have this data sample, you're going to sample one time instant, right? Randomly from 1 to t, anything, just randomly, you just put a random generator, it's going to sample for you, right? Now that you have this random time, then you have your both time tj and j. I'll put this j here to indicate that this j is happening for your sample j, right? When you go for the next sample, again, you sample your time, and that could be potentially different, right? So you're going to have tj here, and now that you have tj, now you can build your xt, right? If you want to build the x at this particular sample time t, you only need to just get your original data, which was x0. You multiply it to the corresponding coefficient. You sample one Gaussian noise, and then you also multiply it to the corresponding coefficient. This is going to be your xtj, right? One sample time at one sample noisy data at time t, right? Now, you have this guy. Now, you can compute eta out of it, right? Because eta was only depending on x0 and xt, right? So you can compute eta based on that. Now that you have the eta, the next thing you are going to do, you take your noisy sample along with the time, you move it forward on your neural network, and at the end of the neural network, you are able to compute your loss because you have the output of the neural network. You have your particular eta at time tj, and then you basically compute your loss, right? And now if you want to compute the gradient, you just backpropagate, right? Now you backpropagate, you have one sample gradient, right? So once you have done it for all the samples inside the batch, then the empirical risk gonna be the average of all of those losses. The batch gradient is going to be the average. I mean, it depends on the optimizer that you want to use. If you're using simple SGD, it's the average of those gradients. If you are using, I don't know, Atom, then probably you need to compute a momentum or something and then average it, right? But at the end of the day, you can use those sample gradients to compute the gradient you need for your optimization. Everybody's cool? So you got the idea how you can compute this loss? Because this is the last trick you need to know to start feeling like you can implement this one, right? And now if you want to do the training is quite simple, right? You have your data set, each time you want, each epoch, you're going to just sample multiple mini batches. Every mini batch that you take, you're going to compute the loss on it, right? Exactly, you do this one. So you sample time and data inside that, and you're going to compute this loss and its gradient out of this by this algorithm, by time sampling, right? Now that you compute the gradient, you have the gradient that you need to update your model, right? Then you're going to just update your model. So your model is going to get updated with that gradient. This is the new weight, and you keep on going till the number of epochs you can, right? And then eventually it's going to converge to something which is, hopefully when you put it on the sampling algorithm, it's going to generate from noise data for you. Questions? Everybody got clear? So the last thing you're going to do is that once you train, you get your model, you put it inside the sampling algorithm, you're going to get the new sample, right? That X new is potentially different from the one you had inside your data set. Questions? No question? So one question, should I go on with the rest of it, or should I stop here? You need a break. Yeah? I go on? Yes? Okay. Okay, cool. Thanks. So you're going to make it easier, so we're going to finish faster. Okay. Now, if you want to visualize the idea, so you can simply think about your neural network in this form. So this is the denoiser neural network that we had, right? So it's going to get xt, the sample at time t, and the time sample t, and then it's going to compute you the mean value, right? This is your neural network. This is the thing that you do. Now, when you are doing the training, how you're going to do this, you're going to sample one x0 from your data set, right? And then you're going to multiply it to the corresponding time sample, right? So you already sampled uniformly time, right? So you do know what is time, so you do know this coefficient, so you do know this one. So you multiply this guy to one Gaussian noise. This is going to give you the noise at time t, right? And then you have your data, and if you add them up, this is going to be the sample at time t, the noisy sample at time t, right? You pass this through your neural network with the time, then this output should be same as eta t. And eta t, you can again compute it directly from this noisy sample and your original data sample, right? So you have your eta t, you have your mu t. You want to make them the same, right? So you want to do it the same. You're going to compute the mean squared error between them, right? This is one instant, one sample loss calculation in your training loop. And then you just keep doing it for multiple epochs till you converge. So despite all the story, this one is not that complicated anymore, I guess, right? So this is easier to understand. But the reason that it's working is because of the whole complicated story we had before, right?